So I'm going to go over a presentation that I covered several times this winter as we had the discussion about protein and yield. Now, I've used a lot of slides from Kansas State from Dr. Romulo Lolato, and so we'll be going through several of that. But in this presentation, we'll cover how is protein in wheat made and some management strategies that will impact that. So one, an overriding factor. Now this is an old slide. This is when I was doing those talks in January, but it's still relevant. Protein is driven by environment as much as anything else. Environment is the ultimate factor. So drought, heat, cool weather, as you're going to learn here in a little bit, are our overriding factors for protein in wheat. Now what we're working in a flat rate pre-plant scenario, as both of these slides. So you have 222 here on the left hand side of the screen in the orange, where as grain yield goes up on the high rate of nitrogen, protein goes down. Same thing as you see on the black and white or the grayscale in the bottom right hand corner, is that as grain yield goes up, protein goes down. Now, a couple things to note on the orange line. So this is all pre-plant, all at the same rate. Effectively, it's saying as you get into higher yield environment with a static flat rate, your protein goes down, which makes sense. When you're fertilizing a lot and get very little yield, you get high protein often. In the grayscale in the bottom corner, you'll see that separation, and those are different environments. So you have the 6 to 8 megagram per hectare. Some really high yielding wheat is significantly lower than the dry land, lower yielding wheat in that 3 megagram. Now, as a basis for all this is we got to get into it, and this is where I start stealing or borrowing Dr. Lolato's data and his slides. We get into the Kansas State. So understand that the wheat berry is made up of 60 to 70% starch. With that, 8 to 15% of that is protein. So majority of that berry is starch. The remainder is primarily a protein, so nitrogen based. By the way, as I go through this, keep in mind that if I say nitrogen concentration or protein, it's the same thing. We actually, to get protein content, we measure nitrogen and multiply it by a factor. So in these scenarios, it's the same thing. Yield, the size of the berry, so the bigger the test weight, typically the more yield when you have the same berry count, is a function of the starch accumulation. The conditions that affect the starch accumulation will affect protein concentration. Now, still going through as we go through these slides, we're going to talk about a few key areas. We have the grain enlargement time that started the protein accumulation about 10 days after pollination. You have 50% of the proteins accumulated into that berry somewhere about day 20. So days after flowering, about 20 days after flowering, and it's in between that milk and soft dough stage. Now your accumulation starts about 11 days after you have pollination. And the duration of these events, so the grain enlargement, the duration is 10 to 15 days post-flowering, where you have the increase in cell numbers, but very little dry, because so you have the cells dividing and increasing, but you really don't have a lot of dry matter accumulation. You have the type A starch laid in a few days after anthesis, which is the large, and then the storage proteins first appear about 10 days into this phase. So about day 10 is where you start getting your protein accumulation. Now during grain fill, your major events in that 20 to 30 days, that's how long this lasts, and it's also about when it starts is about 20 days after flowering. You have protein deposited faster than the starch is being deposited. And this is about 50% of the accumulation of protein or nitrogen will happen about 20 days after anthesis. So that first 20 days, the first 3 weeks effectively, is when you're accumulating 50% of the nitrogen into that berry. Now, during that same time is when you're blending in the proteins of starch type B's. They're small molecules deposited concurrently at the same rate. Now, different precursors via different processes. Keep this in mind. Protein is a source limited issue. So the amount of protein that goes into the berry is limited only by the source. That's the nitrogen in the plant or the nitrogen the plant can take up. On the inverse side, the starch is limited by the sink. So how much starch the plant can put into the berry limits it. It's not the plant's access to the starch, it's the plant's ability to put the starch into the berry. Now this is important because of this. So in the starch, we have 60% of the starch is created fixed during grain fill via photosynthesis. The limited supply is going to be because of drought and disease. Soluble carbohydrates in the inner nodes mobilize to the grain. Zinc limited is limited by the grain's ability to receive those sugars from the leaves. So if something interrupts the ability from the plant to lay in the starches into the berries, that's when it's limited. What's this? It's very sensitive to environmental conditions. What conditions limit our ability to put starch into the grain? Heat, drought. Hot, dry conditions will tend to have smaller berries and lower content of starch in those berries. Now on our protein side, now as a soil fertility specialist, these numbers started shocking me about really where they were. So in the protein part, 30% of the protein in the grain comes from the leaves, 30% from the stems, 10% from the roots, 50% from the glumes. So if you add that up, we're sitting at 85%. So 85% is coming from the plant, meaning you still have 15% that's not accounted for in that berry that's probably being taken up during grain fill. And this says greater than 70% of the nitrogen is absorbed prior to grain filling, meaning up to 30% of the nitrogen in that grain is actually absorbed during grain fill. Now, 30% of that nitrogen in the grain during grain fill, meaning if we limit the nitrogen, let's say we're doing great on nitrogen all the way through flag leaf, all the way through about heading, and right at grain fill we run out. We're going to be low on nitrogen if things are good. It's limited by the source ability to increase protein. Protein is not sensitive to the environmental conditions, but the concentration is. We're going to go into this a little bit further. So the wheat yielding protein, this is Lolato Edwards. This is when Romulo was at OSU working with Dr. Edwards, looking at that yield. I want to point out, so these are the irrigated sites. We get into that 90 to 120 bushel, and it's significantly less. All these have the same amount of nitrogen laid into it. So we put down a whole lot of nitrogen, and we don't yield much. We have really high proteins, 14 to 16%. Although if we're in the 100 plus yield range, it's hard to maintain high proteins. Partially is to get that kind of yield out of our wheat, we have to pack a lot of starch, and those test weights are really high. So we look at low yielding environments, starch accumulation reduced, high protein concentration. High yielding environments, greater starch accumulation. Protein is diluted, you're going to hear this a lot, protein is diluted if N rates are not increased. So what does this mean as we start looking at it? So this has come from some DuPont et al. Papers, and I again got this out of K-State, that's why we have the KSU logo down there. So heat and water stress during grain fill, we have the starch accumulation, we have protein accumulation. On this top, we show the amount of starch if we have heat and water stress. So down here, this red is effectively higher temperature and more water stress. So the further it goes, if we have hot, dry temperatures, we put less starch in the berry. But cool, moist temperatures, good grain fill, greenhouse type temperatures, we really put a lot of starch into it. Look at the nitrogen concentration. It doesn't change. The total amount of nitrogen put in that berry does not change based upon the heat. It's that starch. So if you flip that, you see this right here. If you flip that, decrease total starch, you say, okay, what about nitrogen availability? So we look at the starch up top. We have these two lines. We have with and without N. And so we have the nitrogen with nitrogen up here. Let's go right up here. With nitrogen, the amount of starch. With nitrogen, we have laid in. Without nitrogen, there is no separation. It's the same amount of starch whether we run out of nitrogen or not. So the test weight is going to be identical. Down here, though, we lose out on protein. We run out of nitrogen. Everything's good up early, but we run out of nitrogen. So going back, we might have in this scenario up here, this black is, let's call it a 62, 63 test weight. This red is going to be maybe a 58 test weight because of less starch. On the flip side, because we have a higher test weight up here, we're going to have a lower protein, maybe 12, and this red, since it's a much smaller test weight, and the total nitrogen to a smaller berry is higher, our nitrogen content may be 14 to 16% protein. On this slide, though, up here our test weight's the same, even though we ran out of nitrogen, but we're going to have a difference of maybe 12% protein, and up here maybe it's 14 or 15% protein. So removing nitrogen decreased protein, but did not affect starch. Looking at this, K-State, looking at some data from Ashley Lawrence, saying, okay, looking across our sites, relative yield, can we pick out the right rate for protein and what's that relationship? They look at all these locations and find that 150 pounds approximately is the best in rate for yield, but protein is 170. So you look at that, there's actually a gap. And this is likely going to be the case every time, is that we can max yield, but we may lose out on protein if we don't have that little extra boost in there. That maximum yield and maximum protein are separated by a gap. Now that gap is going to change by environment. It may be a 5-pound gap, it may be a 40-pound gap depending on yield and environment that we're in. But in all likelihood, if the environment is not extremely stressful, there's going to be a gap. Above that is excessive. Now they want to say, okay, could we use flag leaf as an in-season indicator? So they looked at the flag leaf concentration and relative grain yield. Felt, yeah, there's critical levels there. But you know what, folks? I've done a lot of flag leaf concentration, and we look at it, and so we go back here and look at the flag. Sorry, let me get ahead of myself. We look at this. So the flag leaf nitrogen concentration, maxed out yield, the plateau is at 3, and for protein 3.2. Now the scatter on this is too high. I do not tell anybody to go out there and say, hey, go and test your flag leaf concentration. That concentration will tell you whether you need more. Because if you look at these, I mean, just look at this. We have relative grain protein values. We have 4% nitrogen flag leaf and really low grain protein. And up here we have really high protein and low grain leaf. The scatter is too wide. We have too many variabilities that impact the current concentration of the flag leaf nitrogen. Now we can use it as a pseudo indicator, but I just think there's too much scatter to be using the flag leaf as our indicator of how well we're doing on protein. They also look back, can we look at the percent protein from last harvest and see how well we did as far as yield goes? They came up with this and said, okay, if we look at the protein scattered by the yield, we want to be in 11.5 to 12.5% protein to say we maximize yields. Above 12.5, you might say that you over-fertilized. Below 11.5, you might have under-fertilized. That's fair, but there's still too much scatter. I would say it's one of those. If you're into the 13 to 14% protein and you didn't have an extreme drought and you have good berries, you probably over-fertilized. If you're in the sub 10% protein, you under-fertilized, and there's also a chance you left some yield on the table. Now this is the one we start getting into the timing. This is the one what gets us and why you go look out there right now, and there's a lot of wheat that honestly looks yellow, and it's not the drought and not the freezes. We look at this. So we have, this is more K-State. This is come from Lotto and CMPD's work. We have the nitrogen leaf, nitrogen the stem, and nitrogen in the grain in the yellow. At flowering, only 82% of the nitrogen has been taken up. That's flowering, so that's, April. Up there in Kansas, we're talking about April, March, April. Mid-April and later. And that's only 82%. But how many producers are putting on a lot of their nitrogen before zero? And so if we have any environmental factors that have losses, we don't have enough. And by the way, folks, to get good grain in Oklahoma and Kansas, we need one thing: rain. A lot of rain makes grain. So if we have a lot of rain and all of our nitrogen is up front, that's when we get the most losses. Yeah, upfront nitrogen probably worked out okay this year because we've been in an absolute drought and we didn't need it. Drought, you don't lose the nitrogen. So when you get good grain fill and you get good potentials, that's when you need it the most. And we need to go to an in-season. And this is somewhere around that Holliston. This is where you start jointing. We go leaf and we start having some stems. So this is joint right here. Look at that. We're still significantly low on the total use, so we have this whole time frame to potentially play with to get there. Uptake, here's your uptake curve from a different group. This is actually barley, but it shows quite well. Or this is a spring wheat. We just go through here days after sowing. We still have that curve. We're 120. 100 to 120 is that we're talking feet, the hollow stem in there. We go, this is just another the representation between high and low end. The total nitrogen use, and this would be a late planted grain only in Oklahoma. Now this is actually a winter barley, but it fits very well with all the data we have. By tillering, folks, especially the later planted stuff, if you're planting in October, late October, you haven't grown much by jointing. This is where we need nitrogen, but we're putting it on here or here. This is where the plant needs it. Some data coming in, and we're waiting for a year or two, shows that we can absolutely, at least last year, the 16-17 crop could wait for it, and I think we're going to find that it can still wait for it in the future crops. We went out there and had a pre-plant plot that had 90 pounds of nitrogen as ammonium nitrate. We had a check plot, and whenever there was a difference between the enriched strip and the farmer practice, these two right here, they started fertilizing every 7 days of growth out to 63 days after difference. North 40 is around Stillwater, so they saw a difference in November. This is about the second week in November, fertilized all the way to February 20th, with a steady increase in both yield and protein out to February. That's 63 growing days after the enriched strip showed up. Now this plot here, and over here at Perkins too, you see these high. That's where the students messed up, and that is 180 pounds of nitrogen, not 90. So that just shows we were limited, but we have an increasingly growing. Look at the pre-plant, 35 bushel for the pre-plant 90. Up here at February 20th, we're at 55 bushel. We had a 20 bushel increase. Perkins, 45 bushel pre-plant. We go all the way out. We're about mid-February. We're topping out here. We're at 60. We're again increasing yield by 15 to 20 bushel. Our proteins are higher at Perkins. It droughed out a little bit at the end, so we got a little bit higher protein. But look, we still have a steady increase in yield, and that protein maintains constant. We're fertilizing 63 days after response. Lake Carl Blackwell, we had our check, our pre-plant, just under 60. Our showed up on this one. This was about an early December where it started showing up. We fertilized all the way out to March 27th. We are right about the flag leaf. Now you see at this point we're starting to go down on yield. We're actually having a decreasing trend on yield, but our proteins start going up. If we had more nitrogen out here, we would have been pushing these yields to 100 bushel, but 90 was just under. But we go from pre-plant at 57 bushel out to about the end of February 1st to March 1st, we're sitting at 80 bushel. We increase yield by 20 bushel by waiting to when the plant needs it. Now in this case, this site right here, March 9th is right here. We didn't start fertilizing until January and went all the way out to basically anthesis, and you see right at flag leaf. We waited a little bit. This would be about flag leaf right here, actually right here. You get close to flag leaf and you will start losing yield if you waited that long to fertilize. But look what happens. If you really want to boost protein, add 90 pounds at flag leaf of ammonium nitrate. It will do it still. So we got 60 bushel on the pre-plant and 85 bushel, 84 bushel somewhere in the early March. 20 bushel increase, same amount of nitrogen. The plants can wait. We don't have to go before holostem if we have the equipment. We have sprayers. We can go on. If we have a deficiency develop post holostem, that does not mean we are out. We still have an opportunity to gain a lot of ground if we know we have a deficiency and we can fertilize. The catch to it. Similar plots at Perkins. This is 90 pounds. This is a zero fertilized check right here, 90 pounds pre, using UAN streamer. Look at this, 90 pre. Remember at Perkins, I gained 20 bushel by going through the 20th of February. Flat, 2nd of February, and then back to 20. What happened here? UAN streamed on. At this day length, it rained February 3rd. So February 3rd, we have a rain. So source matters. That gets me back. If we go back to this, and producers ask me, what do I do? My strips are showing up, but it's not going to rain. It's better to time your fertility management with a rain than a true deficiency, because we can wait. Let's get it on in front of a good storm system so we make sure we get the best utilization out of that nitrogen fertilizer that we can. Potential. How do we look at this? Don't forget about the grazing. Don't forget about geese. This is a slide I used back in January. Just keep these things in mind. Make sure you have adequate nitrogen for yield potential. Even now, we still got some wheat that's out there that's got a yield potential. And keep in mind that wheat is going to use 1.3 pounds of N per bushel. But we can do better than that. I want to bring this up. This is where the enriched strip really sells itself, is that if we look at Lahoma and look at these averages for Lahoma, so black is the right N rate, orange is the yield, the economic N rate in the black, orange is the yield that year. These blue numbers are the pounds of N it took to produce a bushel of wheat. On average, it was 1.5 pounds of N per bushel, but it ranges from 3.3 to 0. That's why we need the strip, because we don't know how much nitrogen we're going to have. We got to let the environment tell us how much nitrogen we're going to need for that crop. And also, if we're thinking about making protein, if we want to make protein because we have a market for it, again, I want to go back. Enriched strips all season long. Watch it all the way through flag leaf. That means you apply it pre-plant. You top it off. When you fertilize the field, you hit that enriched strip again. Make sure you have a lot of nitrogen there, because guess what, folks? If that strip shows up at flag leaf and that strip turns green at flag leaf, we still have time to potentially make some changes. Now the question we're going to get, because we're starting in flag leaf throughout Chickasha, we got flowering wheat down at Altus and Tipton. What do? Late season in, I get this every year. Late season nitrogen, I want to repeat this over and over again, is a risk and is not a guarantee. It is a risk. It is not a guaranteed practice. But some things you keep in mind. Add about 0.05% protein per pound of N applied at flowering. So at any time, a pound of nitrogen applied to the crop will only, if 100% converted, increase your protein content by 0.05%. So it takes 2 pounds of N to go up 0.1% protein. It takes 20 pounds of nitrogen to increase your protein by 1%. So applying 1 gallon of UAN or 2 gallons of a product that puts on 6 pounds, folks, it's going to get you 0.3% of protein at best. It is about volume. We cannot do better. We cannot physically do better, because it's impossible than 0.05% per pound of N applied. Now, most of my work shows that 20 pounds, regardless of source, is what we need to get that 1% boost. Flowering looks better. This is my data. I've been doing flag leaf and flowering applications since I started my work, and I got done again this year. But flag leaf, I give you a 33% probability that if you apply nitrogen at flag leaf, it will impact protein positively. 33% probability. If you do it at flowering and the environment's correct, I give you, or post-flowering, I give you about a 66 to 70% probability that you can actually increase protein. It's just more of the opportunity. Think about that grain field when it's going to run out. Put a couple pounds on at flag leaf, it may not make it there to the grain field. You're trying to get it there for grain field. We're looking at nitrogen sulfur. There's mixed out there. I've seen some indication that sulfur is going to help us. Sulfur with nitrogen is going to help us at build protein, and just as many sources that says that it could negatively impact. We have a trial on the ground right now called protein progression, where we look at nitrogen timing, nitrogen rate. We have flag leaf plus sulfur, anthesis and nitrogen, anthesis nitrogen plus sulfur. We're looking at all those ways on how we can increase protein and at what level we get the biggest bang. Again, we cannot predict protein. Late N is never a guarantee. And I'll go back to that. If we are hot and dry during anthesis, walk away. Any nitrogen late, when it's hot and dry, will burn the crop. Don't do it. You don't need it, by the way, because remember on those earlier slides, when you're hot and dry, it's going to be a high protein year. It's only in those seasons that we have the greenhouse, the high humidity, the good moisture, all that stuff coming into play. It's only in those years would we think about putting on nitrogen late season, because A, the weather's right for reducing burn because you have good humidity, you have lower temperatures, and B, it's in those environments during grain field that you could have a higher starch load and a dilution of your nitrogen so that your protein content. So again, If at flowering right now this year, if you're at flowering and you're hot and dry, do not think about doing additional nitrogen. It's going to hurt you. We've done enough work at OSU combining nitrogen and fungicides, nitrogen late. In the drought years and hot, dry years, it is a negative toll. It's in those high humidity, low temperature environments that we have an opportunity to potentially do it. Looking ahead at 2018, 2019, this is what we go into. Have a marketing plan. I don't know what's going to be out there this year. We don't know what's going to be. Protein premiums are never a guarantee. It is market driven, but have a place. If you want to manage ground for protein, have a place. Pick your good ground, not all your ground. Soil test, soil test, soil test. Make sure none of the other nutrients are limiting. Plan to invest in nitrogen at the right time. Just because anhydrous is cheap does not mean it's a good source of N, because if we have high yields, it means we had a lot of moisture, and anhydrous early would have been lost. So sometimes investing into more expensive form of nitrogen, UAN, so you can top dress, is better. Variety does have an impact, and we'll show you in a second, but it's not the driving factor, okay? It is not a driving factor. Pay attention to the sulfur. We don't know for a fact how it's going to play out. I'm hoping to get enough data on that, but pay attention to it. Play defense and protect your yield. Don't try to recover. Protect your yield that's out there. That's with the insecticides, fungicides, whatever you need to protect the yield you have. More importantly, scout. Be out in that field. Keep an eye on it. Keep watching. Some pretty cool, exciting work we have coming. I want to focus on 13209 here. The wheat improvement team is working on looking at genetics and nitrogen use efficiency factor in our genetics. And folks, there's some potential. There may be some lines coming out soon that have an ability to produce really good baking and milling quality wheat at lower nitrogen levels and compete at our known, like Gallagher's, and compete with our known good high yielding varieties at better environments. A lot of this work comes from Tipton. We've been looking at Tipton. It's had 300 to 400 lines of wheat down there every year for the last several years at extremely low nitrogen levels. And it's just phenomenal data set, and we're continuing working on that with the wheat improvement team led by Dr. Carver. A high yield low, and just some stuff there. Everybody asks this, what's the variety do I pick for protein? That is not where you ask. First, when you're picking your varieties, does it fit this region? Does it yield in biomass for grazing or grain yield? Does it have the disease packages I need? Do I need soil temperature or pH resilience? You get your set of 4 or 5 varieties. Then you say, oh, of those 4 or 5, okay, this one right here has on average better protein. By the way, that information is all available on the OSU Wheat webpage, because Dr. Marburger has all the protein and baking milling quality from the last several years on that. Well, I hope this presentation was of some benefit and got a little education out of it. Again, many of the slides I borrowed from Dr. Romulo Lalato out of K-State, and I greatly appreciate his efforts in helping me out with this. If you have any questions, here are my contacts. Find me on Twitter, my email, or otherwise. Have a wonderful day.